Okay, so we're moving on to Mayan numeration now. And I said this at the beginning of the last video, but the two numeration systems that we look at in this section are positional, which again means that we have a set of symbols which carry a face value, but then each of those symbols represents a different place value depending on where they appear in our numeral. Now, the Mayans actually did have a number that represented 0 as sort of a placeholder, and I did say that the concept of the number 0 didn't really appear until the Hindu-Arabic system, and that's true. This 0 functions a little bit differently than the way the number 0 does in our Hindu-Arabic system. But let's go ahead and take a look at what we're talking about here. So Mayan is a base 20 numeration system. I like to say that, if base 10 is the or if 10 is the base of most historical numeration systems because we count on our fingers and have 10 fingers, that seems to imply that the Mayans didn't wear shoes, because that means that they could have counted on their fingers and their toes. They used 20 instead of 10. It's kind of a dumb joke, but anyways, I want to point something out about this system. I'm calling it base 20, but modified base 20. And I don't think your book uses that exact term, but that's what I like to call it. And the reason for that is because the Mayans throw in a weird twist in one of your place values that causes all the place values after that to not actually be a power of 20. So here's what their place values represent. If it's base 20, then the ones place is being thought of as 20 to the power of 0. Then you have a 20s place, because that's 20 to the power of 1. You would expect the next place value to be 20 squared, which would be 400, but it's actually not. Instead of multiplying the previous place value by another 20, they multiply it by 18, giving you 360. And then after that, they multiply by 20 for each new place value. So they throw this seemingly random 18 in there, and then say, oh, let's pick up where we left off before and keep multiplying by 20 for each new place value. Why 18 all of a sudden? Well, our best guess as to why the Mayans did that is because Mayan mathematics was really, really closely tied to the changing of the seasons and their understanding of the calendar. They were very, very intimately tied together. And the Mayans had an understanding of the number of days in a year. 360, that's what 18 times 20 is. 360 is pretty close to the number of days in a year, 365. And so what we think is probably the case is that they threw this 18 in here so that they would have a place value for something that's roughly the number of days in a year. That makes their number system more compatible with their calendar. So that, great for them, makes it a little tricky for us to remember that. So we just have to work through some examples and try to get used to that idea. They have 3 symbols in their system, the Mayans, as opposed to the 2 symbols that we saw in the Babylonian system. But that third symbol is this symbol for 0. It looks kind of like a little football with a couple circles near the ends. So that's your 0. 1s are represented by dots. 5s are represented by horizontal lines. And remember, we do things in groupings of 20s. It's a base 20 system. So the way that they group their numbers is they do everything vertically as opposed to horizontally, like the other numeration systems that we've seen. And the bars, the 5 bars, always appear on the bottom, and the dots appear above the bars, kind of equally spaced, as you can see. So let's get a sense for this by working through a couple of examples here. We want to take these numbers and write them in Hindu-Arabic form. Now, the place values here from the bottom up are increasing. So remember, the lowest place value is the 1s place. That would be this place right here, 1s. The next place value up from that would be the 20s place. So that's the 20s place. The next place value up from there is 360, because that's where we throw in that factor of 18. This is the 360s place. Okay? And then how do we read the symbols? Well, 2 bars. Remember, a bar is representing the number 5. So 2 bars would be 10. This is 0. 2 bars and 2 dots, that's 2 5s and 2 1s, which would be 12. So my face value here is 12. It's in the 360s place, so I multiply that by 360. I have a 0, face value of 0 in the 20s place, that's like 0 times 20. Face value of 10 in the 1s place, that's like 10 times 1. Okay? And if we added those up, we would get the number that we're looking for. So let's determine what each of these products are equal to. Let's see, 12 times 360 is 4,320. 0 times 20, of course, is just 0. 10 times 1 is 10. This adds up to 4,330. Okay, 4,330. Moving on to our next our next number. This one, I'm seeing 1, 2, 3, 4 groupings of symbols. So for this, we need 4 place values. You notice after our 360s place, we have 18 times 20 squared, which is 7,200. So that's the 7,200s place right there. 1s, 20s, 360s, 7,200s. Those are those different place values. So working from the top to the bottom, what's the face value of the symbol for the 7,200s? Well, I have 3 dots representing the number 3. That would be 3 times 7,200. 0 in the 360s place, that's 0 times 360. That's a 5 and 2 1s in the 20s place. 5 and 2 1s makes 7, so that's 7 times 20. And then I have 3 dots in my 1s place, which represents 3 times 1. We work each of these out, and then we add up our results. 3 times 7,200 is 21,600. This is, of course, 0. 7 times 20 is 140. 3 times 1 is going to be 3. This adds up to 21,743. Okay, so you notice this process looks very similar from converting Babylonian into Hindu Arabic. And in fact, anytime we're working with a positional numeral system, this is what that process looks like. Multiply your face value by its corresponding place value, so face value times place value, and then add all of the results. Okay, let's keep going. Last thing we want to do, just like we did for Babylonian, is take a look at converting the other direction. So I want to take numbers that are given in Hindu Arabic and convert them into Mayan. Starting with the number 95. So remember, just like we did in the Babylonian case, we're looking at our different place values: 1's place, 20's place, 360's place, 7,200's place, and figuring out which is the largest of these place values that's also still small enough to fit into this number. Clearly 360 is too big. 20 would work. 20 can be divided into 95. So let's do that first. This one I will work out the division just in case you want to see long division a few times for practice. 20 goes into 95 4 times. 4 times 20 is 80. Subtracting gives me 15. So I get 4 with a remainder of 15. That means that this number has a 4 in the 20s place and a 15 in the 1's place because that's my remainder. So we're looking at 4 times 20 plus 15 times 1. So now going from the bottom up, or we could work from the top down if we want, because we know that this is the top. We should have a 4 in the 20s place. That's represented by 4 dots. 2, 3, 4. Okay? 15 in the 1's place. Remember, 15, we're breaking that up into 5s and 1s. 15 is like 3 5s. So 1, 2, 3. It's important to leave some space between my ones place and my 20s place, because if I put them too close together, it's going to look like these 4 dots are stacked on top of this, which would represent the number 19 instead of the number 95, which is what we want. Okay, so that would be my answer in this case. 707, that's the next one. So think through your place values. Ones place, 20s place, 360s place. 360 is big enough to fit into this number, and it's in fact the biggest number that will fit into, the biggest of our place values that will still fit into that. So 360 into 707. Okay, I know that 360 times 2 is 720, which is just too big. So this is going to go in once, and I'll subtract. This should give me a remainder. So this is going to be 347. Okay, that's my remainder, 347. Now, remember, once we've divided, we take our remainder and we say, does the next place value fit into this number? 20 fits into 347. So now we take our remainder, 347, divide it by our next place value, which is 20. All right, 20 goes into 34 once. Do the subtraction. I should get 14, bring a digit down, 7 there. 20 goes into 147. 7 times 20 is 140, and I get a remainder of 7. Okay, so I'm going to have a 1 in my 360s place, a 17 in my 20s place, and then this remainder of 7 is going to be my ones place. Let's write that using place value and face value. So a 1 in my 360s place, a 17 in my 20s place, and the 7 in my ones place. If I did all the multiplication and added everything up, I would have gotten back to 707. All right, let's find a Mayan numeral for this. So I'll just do this to the right. 1 in the 360 place looks like a dot. 17 in my 20s place, that's 3 5s and 2 1s. So 1, 2, 3 5s and 2 1s. That's 17. And then 7 in my ones place, that's 1 5 and 2 1s. 5 and 2 1s. That would be the Mayan numeral for the number 707. Okay, I'd like to do this with one more example. So kind of like that. 32,316. Pretty big number. Remember what our place values are. 1, 20, 360, 7,200, and then we would multiply that by another 20 to get the next place value, which would be 144,000, which is too big. So the place value we want to use is 7,200 here. Okay, now we divide. So 7,200 into 32,316. Okay, so let's see, how many times would this go into this? So if I did 7,200 times, let's say 4, that would be 288, right? And I think that's as much as we can fit. So if I did 4 here, 4 times 72 is 288, and then add 2 zeros, so 288, 1, 2, looks right. Do some subtraction, a little borrowing here. Okay, yeah, 3,516. So that would actually be the remainder then. 3,516. All right. Now, we take our remainder and we divide the next place value into that. So that would be 360 into 3,516. Remember, 360 would be the next place value down. When I look at this, 3,516 is very close to 3,600, which would be exactly 10 times this number. But because it's smaller, I'm suspecting that the answer would be 9. Okay, what is 9 times 360? Let's see, that would be 6, 3, 27. Is that right? Let's just double check that real quick. That'd be 36, carry the 3. Yeah, okay, so we subtract that. Get 6, boom. 400, nope. Nope, that's not right. Let's double check our answer here. 360 times 9. Not using a calculator for this. Oh, I see what I did wrong. 9 times 6 is 54. 27 plus 5 would be 32. So let's do this again. 360 into 3,516. That's going to be 9 times as we suspected. This should be 3,240. Okay, now we got it. There we go. That makes more sense. Remainder of 276. Remember, your remainder should be smaller than your divisor. Okay? This is what I get for not working that out with a calculator or checking my work beforehand. Just winging it here. 360 left me with a remainder of 276. And remember, we go down to the next place value from there. I divide that remainder, 276, by 20. What do we get? 20 goes into 27 once. Bring down a digit. 20 goes into 76 3 times. I'll get a 16 here. That's going to be my remainder. Okay, what does this tell us? This tells us that our number has 4 7200s in it. 4 times 7200. It has 9 360s in it. 9 times 360. It has 13 20s in it, so 13 times 20. And then this final remainder here is going to end up being my ones place. 16 times 1. Now we convert that into a Mayan numeral. So up in my 7,200s place, I should have 4. That's 4 dots. 1, 2, 3, 4. In my 360s place, I should have a 9, which remember we break up into 5s and 1s. That's a 5 and 4 ones. 5 and 4 ones. 1, 2, 3, 4. My 20s place, I should have a 13. 13 is 2 5s and 3 1s. 1, 2, 3. And in my ones place, I should have a 16. That's 3 5s and 1 1. 1, 2, 3, and 1 1. Okay? This will be our last example, and you'll notice up here, this is why it's important to be comfortable with long division, because we need long division. Even me, you know, you can tell I was a little bit rusty here, and I made a mistake. So you got to be careful to make sure you're doing this process correct, and that you're using remainders instead of decimals and fractions, because those remainders are what carry you through the rest of that process. Okay, that's going to wrap it up for 4.2.